Is Professor Leslie Goldberg from Oxford. She's been a leader in counting and lots of other complexity work. Everybody knows her, so I don't need any introduction. So Leslie.
Okay, thanks. So I think it's pretty impossible to follow the Riemann hypothesis, but this is a less deep talk. And I'm going to be talking about approximating the matching polynomial. And this is joint work with Ivana, who's here, and with Andreas Galanis and Daniel Stefanković, which I think also everybody here probably knows. Okay, so actually a whole lot of the stuff that we're going to be talking about has already been introduced this week, but I don't know whether for the online one, so I'm going to quickly redefine everything so that we have the definitions. So what's a matching? We know what a matching is. It's a set of edges, but each vertex can only touch one edges. And so what's the matching polynomial? Well, we know what the matching polynomial is. So if I've been given a graph G, I'm going to use M sub G to denote the set of all matchings of G. So sets of edges that don't touch at a vertex. And the matching polynomial is the sum over all sets matchings of gamma to the number of edges in the matching. So, for example, if I have this little graph, here's the partition function. So there's the empty matching, there's 5 matchings with 1 edge, and 3 matchings with 2 edges, and so on. And we've already seen that this is also called the monomer-dimer partition function. Okay, so what I'm going to, so we've had various talks about this, and in fact, yesterday we had a talk about bounding this partition function. And what I'm going to be talking about today is how difficult it is to do this algorithmically. So the idea is we're going to be interested in, you'll be given a graph G and some fixed parameter gamma, and we'll care about which gamma. And then we want to know how hard it is to approximate or to evaluate at least approximately this polynomial. Okay, so I'm going to start by just commenting briefly on the exact problem. And even if you take gamma equals 1, then this polynomial just counts the number of matchings. And it's been known ever since the days of Valiant and when number P was first defined, that this is a number P complete problem. And it stays hard even if you go down to a bounded degree. So if you go down to delta equals 5 or whatever. So I'm not going to be talking about exactly evaluating this, but rather about doing it approximately. And actually, there's really early work about this. And so going back into the end of the 80s, Jarman and Alistair gave an algorithm for the case where gamma is a positive real number. And they gave a fully polynomial randomized approximation scheme. And it took me so long to draw this picture that I'm going to tell you briefly what their algorithm is. But actually, the reason for showing it to you is that their algorithm has an interesting property that it works for all graphs. So there's no bound on the degree. And that's the last algorithm that I'm going to talk about that has this property. And I'm going to be interested in this talk in what constraints we have to put on the graph. And actually, most of this workshop, we've been talking about bounded degree graphs. And one of my themes is trying to get away from that with deterministic approximation. But let's just go back and look at Markov chains. So if gamma were a positive real number, then what they did is they looked at a Markov chain that samples from the Gibbs distribution. We need the Gibbs distribution anyway, so what is it? Well, it's just the distribution that samples a matching with probability proportional to gamma to its size, so gamma to its size divided by the partition function. On the Markov chain, pick an edge uniformly, and for example, if it's matched but none of its neighbors are, then with some probability kick the edge out, with some probability stay. If you happen to pick an edge that's out and so are its neighbors, with some probability put it in, with some probability stay. And 2 comments about this. So one, if you look at the chain, it's easy to show that the stationary distribution is exactly what you want. And it's harder to see that it's rapid mixing, but that's what they showed. But you can see that it's really important that gamma is a positive real number, because otherwise these transitions don't really make sense. Okay, so to keep in mind then, if the graph is unrestricted and gamma is a positive real, we've got this result. Now, what about deterministic approximation? Well, now what I've got to do is I've got to look at the case where we put some constraints on the graph. So let's suppose, for example, that the graph has a degree bound at most delta. And in that case, there's a deterministic fully polynomial time approximation scheme by a bunch of people. Prasad is here. I don't know whether any other, maybe other authors are here too, I don't know. But anyway, they were able to approximate the polynomial in this case. And their method is correlation decay. And I'm going to talk some about their algorithm, because actually I'm going to be interested in talking about what correlation decay can do for approximating this polynomial. Okay, so in case anybody hasn't seen it, I'm going to tell you what does that even mean. So here we've got this partition function. We want to approximate it. I say we're going to use correlation decay. So I'm going to tell you what that is. And by the way, if anybody has questions or hasn't seen it, feel free to ask. Okay, so correlation decay then. So I've got a couple slides, correlation decay 1, 2, 3, and so on. And kind of over the course of the talk, I'm going to kind of try to tell you a little bit more and a little bit more. And hopefully, if you haven't seen the method before, then you should know how to use it by the end of the talk. So that's kind of a goal. Okay, so the first little snippet is that if you wanted to approximate the partition function, it would really suffice to approximate the marginal probability. And here it is a probability, because we're still in the case that gamma is a positive real. So what do I want to do? So I want to define z of g minus v of gamma. So that should be the contribution to the partition function due to all matchings in which v is not matched. So the sum over all matchings that don't match the vertex v of that. And so the marginal, the v unmatched divided by the whole partition function, we're going to call that PV of g gamma. And so clearly what that is that if you sampled a matching from the Gibbs distribution, that would be the probability that this particular vertex v isn't matched. Yeah? Okay? And okay, the first claim that we need for correlation decay is just that approximating this probability is actually the same as approximating the partition function for all practical purposes. And the reason for that is that you could just pull the z up and the p down. Actually, I think I wrote it somewhere here. And so the partition function is just the partition function with v unmatched divided by the probability. So if you could estimate the probability and you wanted the partition function, all you would need is one recursive problem. So that's a really efficient thing. So if you could approximate this probability well, then you could recurse and so on. So we just need to approximate the probability, and that's all that we need to do. Okay. Second fact about correlation decay is that if you really want to estimate the partition function, it actually suffices to estimate it on a tree. You don't really have to consider a general graph. And in the case of the matchings polynomial, this goes back to Godsell in about 1980. And this fact's not very hard to show, actually. But what he showed is that if you take a graph, like maybe that one, and you want to calculate the probability, this marginal, so the probability that v is out, then it's exactly the same. I mean, formally it's the same. It's the same polynomial, well, same rational function, as what you would get if you estimated the same marginal in the self-avoiding walk tree, which is just the tree where you start from G, you start from V, and you just enumerate all walks from V that don't visit itself. So, you know, from V you can go to U or W, but once you're at U, without going back, you can only go to W, and so on. And okay, for some reason I wrote down the polynomial for this particular graph, but if you want to prove that it's the same. I mean, it's always the same. And I mean, just algebraically, it's the same thing. OK, so if you wanted to estimate this marginal on a graph G, all you would need to do is to write out this self-avoiding walk tree and estimate, from that vertex that you care about, and estimate the marginal probability there. OK, so that's good. And then the good thing about trees is that they're really easy to work with because we have natural recurrences. And later in this talk, we're going to need the particular recurrence for the matching polynomial. So I've gone ahead and written it out because it's nice and easy. So let's suppose I had a tree, maybe the self-avoiding walk tree, and I've got some vertex v and some vertices below it. And let me use ti to note the tree below vertex I. Then let's just try and write down some of these things. So what is the partition function for the matching polynomial, given that v is not matched? Well, if v is not matched, then I can do whatever I like in the ith subtree for all of them. So this partition function is just the product of the partition functions at all the subtrees. But if I wanted the whole partition function, well, either v could be unmatched, or else for one of its d children, I could match v to the child, so I get a factor of lambda for that. Then I better look at the recursive polynomial corresponding to the child not being matched, and everything else can do what it likes. So that's straightforward. And the reason I wrote those down is just that if you would write down the marginal, so which is the v not matched divided by everything, and if you would just look up there and divide, I mean, you have to do it, but supposing you chose to divide through by that thing, what you would immediately get is that the marginal for the tree at v is equal to 1 over 1 plus gamma times the sum of the marginals of the children. So we got this. Oh, and of course, if your tree has just got one leaf, then the marginal is 1, because you can't match it, because you haven't gotten an edge. OK, so we got this nice little recurrence that one vertex, the marginal is 1, and otherwise, if you just sum them up, multiply by, OK. OK, so if you wanted to compute this thing on a tree, you clearly could. So far, this is an exponential time algorithm because the self-avoiding walk tree is exponentially big. So that brings us to the third little principle of correlation decay. And that says that if correlation decays, and we'll see what that means, then what you do is you don't write down the whole self-avoiding walk tree. Rather, you just truncate it to depth log n. You pretend you knew all the marginals at depth log n, just pretend they're 1, and then compute. And then it's an easy calculation. And correlation decay means essentially that the error decreases geometrically as you go off the tree. So at your truncated leaves, obviously, you've got vast error because you just made up the answer. But one level up, it's a little better. One level up, it's a little better, and things multiply. So by the time you get to the top, you actually haven't got much error. OK, so that's correlation decay. And these guys, using that, they managed to give them a deterministic approximation scheme for bounded degree graphs. And we keep seeing this, and I guess I don't know whether anybody's actually explained it, but it just means that you input a graph, and you input an epsilon, which says, how accurately do you want to approximate this thing? So maybe you want to estimate it within a factor of 1 plus or minus epsilon, and the runtime you're allowed is a polynomial in the size of the graph and also in 1 over epsilon. So you're allowed more time as you need more and more accuracy, but only polynomially so. OK, so that's the positive real case. But what if gamma is negative or complex? Actually, I edited my slides last night because at this point in my slides, I had about 3 pages explaining why you should care about complex, and I've erased them because that not needed for this meeting. But anyway, what if gamma is complex? So the method that immediately comes to mind in this case is what was being called the Barvinok philosophy for some reason at this meeting. So what is the Barvinok philosophy or algorithm? Well, actually, we know, I'll do this quickly because we've seen it before. So look at our polynomial. Okay, it's a polynomial. The degree is not too high. Certainly it's at most, wow, it's at most n over 2 or whatever. So I suppose I can find an open set in complex plane where the polynomial is not 0. Then within the domain, the log is close to what you get if you truncate the Taylor series to log n terms. So that would give you immediately an n to the log n algorithm for estimating the polynomial. And then there's a missing piece supplied by Pato and Regitz, which kind of get clever algorithm for computing these log n coefficients. So as long as we have a zero-free region, we actually get a polynomial time approximation algorithm. And then, well, going back to Elliot's first talk, this come up in just about every talk in this meeting, we have this kind of really important and well-known result that for this polynomial, we know that actually the zeros only occur on the negative reals. And actually, beyond that, we've got a bound. So the zeros occur on the real axis, and actually they're less than -1 over 4 delta minus 1. So everywhere apart from this negative real axis, we get a good approximation algorithm. Okay, so due to Pato, Regitz, Barvinok. Okay, so the first piece in our work was just a kind of filling in the rest. So obviously, Ivana's slide have all the cardioid and amazing pictures. I couldn't think of many pictures to draw, so a couple axes. So here what you have is easy, 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 easy. And one thing we did is to fill in the rest of the picture. So what we showed is that actually if you pick gamma to be any negative number less than this threshold of -1 over 4 delta minus 1, then actually the approximation problem is number p hard. And this is something that Ivana was asked about, but well, because we have negative numbers, that's why you can get such a strong form of hardness. What this means is that if you fix any very negative gamma, and you're given a graph with degree at most delta, and you want to approximate this polynomial, it's so hard to do that even if you approximate it, you would actually exactly solve some number p hard problem. So this is a very strong form of inapproximability. Okay, so I want to say a little bit more about. So I've said if you approximate the polynomial, well, it's not there, the polynomial, but what does it mean to approximate a complex number? So what do I mean approximated? And well, we mean a few things. So one thing that's number p hard is approximating, well, here we're on negative real, so actually this is a real number. So one thing that's hard is approximating the absolute value of the polynomial within, I put here a factor of 1.01. So getting within 1.01 of the right answer is hard, number p hard. And if you remarked this 1.01, we more or less just made it up. It's not important at all. So you could replace it with any number you like. So getting within 100 of the right answer, a factor of 100, that's number p hard. And actually, if you felt like it, you could power it up, and you could show that getting within 2 to the n to the 1 minus epsilon is number p hard. This is not exponential, and that's a little bit interesting. We don't know whether it's hard to get within an actual exponential, and for some inapproximability results that is known. So that, but anyway, but you can power that up quite high. Another remark I wanted to make is that the hardness works even if G is bipartite. Okay, whatever. But also, we can restrict G not to be a 0. And I think that's important because all of these approximations are relative. And so if I say, gosh, you've got to get within 1.01 of the right answer, and then I give you a graph which happens to be a 0, then obviously you would have to hit it on the head. So there's not much difference between approximation and exact, but you can you can restrict to graphs that aren't zeros, and you still got the hardness, so there's no kind of weird cheating going on there. Okay, so that's hard. And then the other thing that's hard is the partition function is it's a real number, and deciding whether it's positive or negative is similarly hard. So approximating the arg additively, I mean, just to the extent of determining whether it's a positive or negative real number. Okay, so that's the summary for bounded degree graphs. Now, our actual objective in this paper was not to stick to bounded degree graphs, but to try to figure out how we could go, well, okay, to fill in for the complex plane, but within the context of the complex plane to go beyond this. So I want to take a little excursion and talk about relaxing this max degree requirement. And actually, most of the results that we have, not just matchings, but all these kind of inapproximabilities, there aren't many results that aren't in these deterministic approximations that aren't about max degrees. So that's kind of, and you'll see, we don't, so there's lots of open problems. Something I was asked about just last week was all these kind of, there's a concept of average degree, this nowhere dense. And somebody asked me whether I thought that we might be able to do things like that. And I looked at it in the, nowhere dense is a graph class that includes all sorts of stuff like, for example, planar would be way below it. So I think there's a long way to go before we could tackle anything like that. But what we did do is we looked at the connective constant, which had already been studied for the positive reals by Sinclair, Srivastava, Stefanković, and Yin. And okay, so I'm going to tell you what so you might have seen connective constant for infinite graphs, and they studied it for finite graphs, and the definition is essentially the same in what you expect. So this looks ugly, and I've put it there just because we'll need it, but I want to just talk you through what does it mean, because it's really natural. So let's look at the number of walks, self-avoiding walks, in a graph from a particular vertex. Okay, so if I had a delta degree bounded graph, and I asked how many self-avoiding walks there were of length k, well, of course, there would be at most delta to the k because of the bound on the degree. Okay? And if I asked you how many walks there are of length up to k, well, still, it would also be at most about delta to the k because the shorter ones don't matter too much. Okay, now the connective constant is almost that, just summing how many self-avoiding walks there are up to some length L and demanding that it be about delta L. The only difference is that we don't care about short walks. So you could have a vertex of degree n. Who cares? That would have a whole lot of walks of length 1, but we're only going to start counting once you get L to about log n. So connective constant delta, a family of graphs has connective constant delta, if for any length we want to focus on, which is at least some constant times log n, the number of self-avoiding walks up to that length is at most delta L, and there's another constant there, but not too important. So roughly delta L walks of length L as long as L is big enough. Okay, and the rest are just constants, they don't really matter.
Leslie, are there examples other than fixed degree, other than bounded degree?
Yeah, I mean, natural, I mean, sure, I'll just add a vertex stupidly.
The random graph.
Yeah, the random graph, that's a better answer.
Oh, okay.
I nominate Will to answer all my questions. Yeah. I mean, yeah.
Random sparse.
Yeah. So I mean NP, so you get, yeah. Okay. Any other questions? Good. Okay, so that's the connective constant, and if you forget all these symbols, just remember that A and C are some constants. I put them in just because that's how the results are going to get stated. So a family of graphs has connective constant with delta with this profile A and C if all this rubbish. And so they're constants there. Okay? Okay, so what do those guys do? Well, they showed that for fixed delta, when gamma is a positive real, then you can approximate this on graphs with connective constant at most delta. And this profile stuff doesn't really matter for them because it's just a positive result. And no bound on the maximum degree. So this is the point. So the connective constant is bounded, but the maximum degree can be arbitrary. And the runtime, well, we noted already that an approximation algorithm should have a running time. It's polynomial and n over epsilon. And I put the rest of the junk in just to indicate that it depends on these parameters. We're not going to improve that in the constant case. We're just going to match it, but I just put.
The delta, it has some spectral characterizations like spectrum radius with some metrics.
I mean, just think about it as the number of walks. The number of walks. Your essential branching.
It's probably inverse to the distance of the nearest root to the origin. That's what it is.
What? You think?
It's the inverse of the distance to the nearest root of the nearest root to the origin.
But that's the number of tree-like walks.
Yeah.
And that's not necessarily the same as the number of self-avoiding walks, right?
Yeah, I don't think that's going to be true. Okay, okay, so they use correlation decay, and we're going to too, but one thing that we tried that we weren't able to do that I think is really interesting is that we didn't, maybe we didn't spend long enough and maybe someone else can do it, but it would be really interesting to know whether this Barvinok, you know how to do it?
But we talked about it. It's not my idea. I heard from somebody, somewhere, that this bound gives you the distance of the root nearest to the origin. This the connective constant.
But it gives you
for matching polynomial.
Yes, yes, because all the roots are negative real.
They are.
It's not my idea. I heard it from.
Okay, so why I think it's not true why I think it's not true is that jumping ahead, you can create connective constant whatever you like. Like, you know, the roots on the real axis are all this, you know, -1/4 delta -1.
So it doesn't have anything to do with like the sum or the power sums of those roots?
Well, so for example, I can take, and this is like jumping ahead, but who really cares? I can take a cubic graph, yeah? And suppose I take a cubic graph and then I replace each edge with a huge tree, yeah? Just
replace
each edge with an enormous tree where the two leaves are really, really far apart. Then what I'm doing is I'm decreasing the connective constant of that graph as low as I want. Because imagine that you want to take walks in that graph. And now, if you wanted to traverse an edge, you have to go through this tree. But what you do is more or less forced, because you're walking from a leaf to a leaf. And so I can push the connective constant down practically to 1, which is why if I just, I'm going to come back to this, but if I just jump ahead, the hardness results for the connective constant are delta bigger than 1 rather than cubic. That's just, and that's because you can take a root for the cubic thing and shift it and still have really small connective constant. I don't know if that makes sense. It makes me think that we might take it offline, but
sure. I'm sorry.
I don't know. Okay. I'm just saying you can make the connective constant really, really low, and so even though there, okay, what was I trying to say? I'm trying to say even though there are roots in this range, you know, above -1/4 delta -1, I can still make the connective constant really, really small, down towards 1. But anyway. Okay.
Sorry.
Yeah, okay, anyway. Okay, and something that would be interesting to do, that I don't know how to do, and we talked about this only briefly, but it'd be really interesting to try and figure out how to use the Barvinok and Patel-Regitz method for connective constant. And here's why I don't know how to do it. In order to compute the coefficients, what you need to do is you need to enumerate the graphs that contain a particular vertex that are of a certain size, like log n. So if the graph is bounded degree, then you can do that. So it's a bounded degree graph, and so if I want to know how many connected subgraphs are there that contain my vertex v, well, it's like v to the whatever length. So that's delta to the whatever length. It's small. So I take, but if I were in connective constant, I mean, I could have if I wanted to, I could have a vertex, with very high degree n or whatever. And then, I mean, if I wanted to know how many size k subgraphs containing this vertex, well, obviously there's n choose k, and so it grows too big, and you kind of need to enumerate them. Okay, so we don't know how to do that. So I think that's an interesting question, and maybe one that should be explored at this meeting. But what we did in this paper is we just went around that, and we used correlation decay. Okay. Okay, and then one thing I want to point out is that, unlike the bounded degree case, we can't push the algorithmic result to this zone where you've got negative real numbers, which are above when the roots start, and that's kind of because of what I was talking about, that the connective constant. Okay, and so the connective constant hardness result then is that for any delta bigger than 1, and whatever profile, if you take one of these, if your connective constant is at most delta, then the same things that were hard before, I shouldn't have put all that junk on the slide, are still hard. Okay, so that's hardness. And then what we wanted to do was say, okay, I didn't tell you the most. Okay, this bit I put in red to remind myself to notice it, and I forgot. We didn't show hardness on the whole negative axis. What we showed is that there's a set of values, and I'm going to show you which ones in a minute, that are dense on the negative axis for which it's hard. So the conjecture would be that for any gamma that's a negative number, that the problem is hard for a connective constant, but we didn't show that. We just showed that there's a dense set, dense over the whole negative axis. And the reason for that is because we had zeros to work with. And I mean, there are probably more ugly zeros not based on nice regular trees everywhere else. And so the conjecture would be that this would just be true, but we didn't prove that. So we just proved that, for any gamma, go as nearby as you like, and there's some more hard. Okay, and then we do get an approximation algorithm off of the negative real axis, and that's based on correlation decay. And I put in the runtime. I don't know if you really care, but the bottom line is it's kind of, I mean, we borrowed loads and loads of things from the paper on the positive real axis, so it's hardly surprising that we got what would amount to the same running time so it's kind of it's a generalization rather than it doesn't improve anything there. Okay, good. And so what I wanted to tell you is that there's an algorithm that takes as input a graph and an epsilon, and what does it do? It approximates the partition function up to some factor e to the z, where z's a complex number with norm at most epsilon. This is kind of the natural way to generalize if you write your f-pres in one particular form. But of course, if it looks a little bit strange, it doesn't really matter. So if same thing, you could approximate with you could approximate the norm within any multiple, or the arg within any additive factor. Okay. So that's the connective constant. We use correlation decay, and what I want to do next is talk a little bit about, I'm not going to run through the whole details of the correlation decay, but I'm just going to kind of highlight what were some of the issues for us. And the main issue was actually how do we, I've already hinted that when we do correlation decay, we have to have the distance between the marginals at some level shrink as you go up, and that's still true. And we had some issue with how to actually measure these distances in the complex plane in such a way that it would work. And Jan has already talked to us about using correlation decay in the context of the hardcore, and he talked about this green circle that came up on a number of slides. Sorry, I'm standing right in front of it. A green circle that came up on some of the slides. And actually, Jan talked a lot about the multivariate case, but actually what they were doing there was correlation decay in the complex plane. Because they were working, they could kind of measure distances using the norm, and that didn't work out for us, so we had to work a little bit harder. But I also want to mention out that Peters and Rex have also essentially proved contraction. So there are various ways you can, the point of these slides is just to say that there are various things that can work. Okay, correlation decay, the marginal is not now a problem. A lot of the stuff I just put it up as a reminder, but it's not new, so you saw it before, you don't have to read it. So remember, we're trying to estimate these marginals. Now they're not probabilities because we moved into the complex numbers, but that doesn't matter. Now, what we do when we do correlation decay, normally what we want to do in order to truncate the tree is to say, well, if the marginals differ by some amount at one level, you know, maybe I've got some marginals here and there, and I run a step of the recurrence. How does it go down? Maybe by some factor. And so, of course, there's the question about how to measure distance. And if you got really lucky, then, you know, the L infinity distance on the marginals themselves would shrink, but why should it? That's a little bit too much to ask. And so what people do, if you haven't seen this before, unsurprisingly, it's a little bit of a kludgy area. You know, we come up with a potential function, and instead of measuring the distances between the marginals themselves, we measure the distances between their potentials. And so, of course, what you do is you apply the recurrence to the, well, your potential function better be invertible so that you can put it back, apply the recurrence, and measure the new distances. As long as that goes down, that's fine. You still get a choice for how to measure the distance, and a lot of work uses the L infinity norm. And I just wanted to kind of show you, in case you didn't see it before, what's the standard thing. Okay, so you've got these distances, yeah. You've got some potential function. Maybe you hope that now, given the potential function, that the distances will go down. And blah, how are you going to do that? Now you just use the mean value theorem, and you know that there's some point between the potentials here and the potentials there, such that the difference in potentials at the root is just the derivative of blah, yeah, everything you have to do. Okay, so that's not very interesting, but the point is that what you can do then is you get this formal, you get this essentially the derivative of the recurrence applied to the potentials, and you want to show that this thing is bounded. And if you do that, you know, bounded by 1 minus epsilon. Okay, so that's the gain. And when Sinclair et al. Looked at the positive reals, I think this is the only paper maybe that does this, or at least the only one I saw. But I mean, they make the following argument: look, connective constant it's a global thing. It's not a local thing. Something can go wrong locally. So L infinity is a bit stupid as a distance measure, and probably better use some other norm. And the norm they chose depends on the various parameters, on delta, that's the connective constant, on gamma. And so kind of what we did to get the algorithm to work was to try to figure out how to generalize their choice of norm and their choice of potential function, which I've written here, to the complex case. Okay, but how do we, so how much time do I have? Okay, so I have 5 minutes, so I'm just going to sort of talk briefly about this. So how do we measure the distances to do contraction? Well, I won't go through the details, but it's going to turn out useful to reparameterize. That always happens here. So instead of looking at these marginals, what I'm going to do is I'm going to take gamma, and I'm going to reparameterize it as 1 over some value, the square of 1 over some value q, and q, the real part of q is going to be positive, and these pictures are just to spare you the trouble of working out whether that makes sense, and it makes sense as long as gamma is not a negative real, which of course it isn't because the roots are there. And once you reparameterize everybody that way, then the first step is going to be figuring out when you apply the recurrence, where do these x's actually live? And it'll turn out actually that they live in an open disk, well, a really nice open semicircle, so which is just the radius is 1 over the real part of Q, and that's not very hard to show. So that was the purpose of the reparameterization. And then the way we measure the distances in order to prove contraction is a kind of a standard way of measuring distances. So if I have any open set, such as the semicircle in which we work, and if I have any curve, eta, that just maps 0, 1 to some point, from some A to some B, then the length of eta is just what it is, the integral. And if you applied a function phi, mapping u to the reals, then you could get the length with respect to phi by integrating that. And that would depend on the derivative of phi. And then we define the distance just to be the infimum. So the distance with respect to some potential function, which we're going to choose, just to be the infimum over all etas of the distance. So, okay, so what do we choose? So the potential function phi that we choose, it's kind of the derivative of this map applied to the messages, is, well, okay, so it's essentially, if you remembered 1 over x times 2 minus x, it's like that, but working on the real parts. And it needs to be greater than 0 in order for this distance measure to be a metric, and actually also it needs to be bounded because this is going to come in. But okay, I mean, I don't want to belabor the point too much, especially because I've not got much time left. But okay, anyway, if you measure the distances this way and then you use the Q norm that would be the right one, you get contraction. Okay, so I want to not say any more about that. I want to close by just, in fact, I don't need a slide for this, so let's just park it. I want to close by just saying a little bit about the hardness result. So the hardness says that there's a dense set on the, well, okay, the hardness result says that for the bounded degree case, for every gamma, which is less than minus 1 over full delta minus 1, you get number p hardness, and that there's a dense set where you do for the connective constant, and that goes down to delta's 1. So how does the hardness go? And it's a little bit like what Ivana was showing you in terms of the hardcore polynomial. So in order to get hardness, what we show is that if you start with any gamma in there, then big rigmarole, what you can do is basically mimic any edge activity. So we move to the multivariate case by showing that with the fixed gamma that you're handed, you can actually mimic any gamma you like. So if the user hands you a gamma, you can build a gadget that looks just like that gamma. And by just like, I mean so much like that the error is exponentially small. And so that's a big rigmarole, and doing that involves looking at the zeros and either, okay, well, it looks like this. First, you show how to get reasonably close to every gamma that you might desire, and that's done by some gadgetry. And then there's a kind of bootstrapping, which is these kind of maps that power it up. And having done that, you now are in the position of knowing that these gamma values enable you to mimic pretty much any edge activity you like. Then we know some edge activities are hard to compute exactly, like minus a tenth, I think is the one we chose. And we show that by doing some kind of binary search, you know, taking some edge and repeatedly changing its value, we can actually just narrow down that and compute it exactly. Okay, so in order to close, the one thing I wanted to show you, if I can find it, blah, blah, yay. I wanted to show you what is this dense set, just in case you're interested. So which are the ones that we actually show hardness for in the connective constant. And you can see it's just essentially the set of reals for which regular trees give you a 0. Okay. So it's the set of reals such that gamma is minus 1 over 4 delta minus 1. You recognize that. That's where the roots start. Cos theta, that's just for some rational multiple of theta. And the point is that if you are not in there, then the regulatory of theta is not 0, but if you're in there, it is, and that's helpful. Okay, so I think I should stop.
Any questions?
So what about claw-free? We had some stuff in our paper about how there's a special case of independent sets and claw-free, but...
Right, so in fact, yeah, in Patel and Reg, it also applies actually for independent sets and claw-free. I cast it as matchings just because that's what we are looking at. Our thing, so we didn't look at that, so I don't know whether we can generalize to that. But well, I mean, obviously the hardness goes through, but we didn't look for the eviness.
So question will be about maybe some other alternative. So there are all these high temperature expansion stories, and there is this algorithm in statistical physics called worm algorithm. Right?
Oh, okay, yeah. I know.
There are some efforts for some problems recently, right, coming from this approach, and potentially it can also fight high degree, right?
Okay, but how?
Any comments on that?
Oh, okay. So my comments are mostly based around ignorance. So I've seen the worm algorithm, and I've certainly seen it when the parameters are positive and real. I don't know what the algorithm is when the parameters are complex, but I guess you're telling me that's all well defined and.
Possibly, yeah.
I mean, it's a Markov chain essentially.
It's Markov chain.
So I have to have transition probabilities.
Yeah, but it's a complete. Well, it's mapping to different space, right?
So you map the whole thing onto the positive reals or something?
Oh no! I mean your state. So it's not matchings, but will be some other space. So you'll basically be jumping from well, jumps will be much more significant than just flipping.
So I think the problem for us here is because the parameters are complex. It isn't that we don't know how to prove mixing, is that we don't even know how to define, you know, these are just complex, the weight of an individual configuration is complex. I know there's this kind of quantum Monte Carlo stuff, which I don't know much about, which maybe enables that. But anyway, maybe you should tell me about it. I'm interested, but I don't know. Yeah.
Any other questions? Thank you very much. So we are a little bit behind, so we'll come back in 5 minutes.
Oh.